Welcome to your premier destination for mastering concepts. Crack IIT, NEET, and all board exams with us.
Mirrors as simple, impenetrable surfaces. You stand in front of one, light hits the glass, and your reflection bounces straight back. But if you take a single candle and place it at a sharp angle against a thick glass mirror, that simple assumption breaks down. Look closely at the reflection. You don't see one clean image. Instead, you see a chain of faint echoes trailing deep into the glass. If you isolate the very first image in that sequence, the one bouncing off the surface closest to the candle, it is surprisingly thin and dim. Yet right behind it, the second image in the chain carries the most visual weight, appearing significantly sharper and brighter than the reflections on either side. Light bouncing off the closest physical boundary is drastically weaker than light bouncing from deeper inside the object. This microscopic cross-section reveals the mirror's true physical anatomy. It functions as a two-part system. There is a thick pane of transparent glass in the front and a polished silver coating hidden in the back. When a beam of light from the candle travels toward the mirror, it first strikes the front boundary of that glass layer. Standard glass is a poor reflector. Only a tiny fraction of the incoming light, exactly 4%, bounces off this initial physical boundary. This 4% surface bounce creates image number 1. It is the direct mathematical reason that the closest reflection appears so faint. The physical surface you touch when you wipe down a mirror is only responsible for the weakest, most insignificant part of the reflection. The remaining 96% of the light energy breaches that front layer and travels through the transparent pane. This main wave of energy travels through the glass until it hits the polished silver coating at the very back. The silver layer is the engine of the mirror. It bounces almost all of that 96% light energy backward, pushing it back out through the front glass. This return of light energy forms image number 2, which is why the second reflection in the chain contains the most visual clarity. As that wave exits the glass, a tiny fraction hits the inside boundary of the front pane and fails to exit. It bounces backward, internally. This creates a pinball effect. The trapped light zigzags between the front and back layers. With every strike against the boundary, it loses energy, forming images 3, 4, and beyond. That infinite chain of fading phantoms is the visual record of light energy slowly bleeding away within a closed system. Step back from the physics and look at an everyday mirror. The mirror functions as an intricate optical trap, designed to split, delay, and diminish incoming light. When you look into a thick mirror, you are actually peering through a transparent barrier to see what is happening behind it. The clear reflection you rely on every morning is a secondary echo. It is light bouncing off a hidden, buried layer of silver, a mechanical process happening invisibly right in front of your eyes.
Thank you for exploring the universe with us. Subscribe to Fundamental Physics for more.